The last thing we're going to look at with our exponential growth and decay models is this idea of radioactive decay and half-life. So when you are looking at certain elements, okay, or certain isotopes, they are unstable in their state. So they're going to decay over time. Um, this also applies to things like drugs in your bloodstream. So if you take a Tylenol or you take an ibuprofen, it's going to decay over time in your bloodstream as well. So we're going to look at this idea of half-life that comes along with it. So to illustrate what I mean by half-life, let's go ahead and take a look at an example. So this is telling us that the half-life of ibuprofen in your bloodstream is about 2 hours, and you take a 400 milligram pill of ibuprofen. All right, so what this is basically saying, okay, is that you're starting off with an initial amount of 400 milligrams in your bloodstream. Now, the half-life means that after this amount of time, after 2 hours, the amount of ibuprofen that's in your bloodstream is going to be cut in half. So after 2 hours, you're going to have half of that initial amount, or half of the 400, which is going to mean you now have 200 milligrams in your bloodstream. So then after another 2 hours, so if you go up to 4 hours, you'll have half of that again. So you'll now have 100 milligrams in your bloodstream. Or again, if you go another 2 hours, you're going to cut that in half one more time, and you'll have 50 milligrams in your bloodstream. So this idea of half-life is saying that after this amount of time, you're going to cut that initial amount in half, and you're going to cut it in half again and again and again and so on. Now for this one, it was pretty simple. We had pretty easy numbers to deal with, and we could just cut them in half and figure it out. But when you're looking at more complicated examples, or you want to look over much longer periods of time, it's not realistic to just go through and cut it in half like this every time, but you want to actually build an equation, build a model so that you can plug your values in. So let's go ahead and look at this carbon-14. Okay, so carbon-14 is one of these unstable isotopes. It decays over time. Carbon-12 is the normal state of carbon. So with this, we can see that it has a half-life of 5,715 years. So with carbon-14, because it's known to be unstable and it decays over time, you can use it to date things. So if you're an archaeologist and you find some sort of painting or you find some sort of ancient pottery, you can use carbon dating to figure out how old it is, at least roughly. You can get an idea. So this is telling us that our half-life for this is 5,715 years, so that's going to be our time that we'll be using. And our goal here is going to be to build an exponential decay model for carbon-14. So just like we were using in the last video, our general model for either exponential growth or decay is A of t is equal to A naught times e to the power of r times t. Okay, now notice on this one, it doesn't give us a specific initial amount. We don't know what A naught is for this problem. So we're just gonna have to leave it generic for now, okay? So the only thing that we really do know is that after 5,715 years, we are going to have half of our initial amount. So basically that's saying in this time period, our A of t is going to be half of our initial A naught. So we can go ahead and plug this in then. So we'll have half of A naught is equal to A naught times e to the power of r times 5,715. All right, and we're going to have to solve for the rate because we don't know that yet. We need that in order to build our model. So just like any other exponential equation, Isolate your exponential term by dividing by the a naught, and we'll get half is equal to e to the power of 5,715r. From there, we can switch it into log form. Remember, the log with a base of e is a natural log. So natural log of 1/2 is equal to 5,715r. And then just divide by the 5,715. And we come out with an r value that's approximately negative 0.000121. Okay, and like I told you in the previous video, when you're solving for these rates, always make sure you keep plenty of decimal places, at least 5 or 6 decimal places, because the more you round, the less accurate your final answer is going to be. All right, so putting this all back together, we are going to get a of t is equal to a naught times e to the power of negative 0.000121. Okay. Now in this one, like I mentioned before, we just left our initial amount as a naught because we weren't given a specific value. But say we were given a specific value like we were up here, in the previous example, right, we knew that we were starting with 400 milligrams of ibuprofen. Well, if we were trying to build a model for this example, then we would have actually used A naught equals 400 and plugged that in. So if you're given an initial value, plug it in like normal. But if you're not, then that's when you just leave it generic. So that's going to be based on the problem and what information you're actually given to start with. Okay, so now the second part of this is we have a painting that was discovered that contained 96% of its original carbon-14, and we want to try and estimate the age of this painting. Okay, well, if this is saying that our painting has 96% of the original, what that's telling us is that our A of t is 96% of A naught. 0.96 times A naught. So we can just plug that into our model that we found in part A. So we are going to have 0.96 times A naught is equal to A naught times e to the power of negative 0.000121. Oops, and I just realized I forgot my t up here. So 121 t. All right, and then just solve for t. So divide by the initial amount, which of course both of these just cancel. Well, 0.96 equals e to the negative 0.000121 t. Switch it into log form. That becomes natural log of 0.96 equals negative 0.000121 t. And then just divide by our rate, and we will end up with approximately 337.4 years. Okay. All right, guys, so that is it for our exponential modeling and with both the growth and decay. There was one additional example that I posted in the notes on Blackboard that you can look through, but other than that, as usual, make sure you go through the lab, go through the homework, and email me if you have any questions.